Great. So yeah, so good evening, guys. I'm Xiang, and I'm here to talk about the moon forming impact and how we can deduce some properties of the moon forming impact using data from Venus. And so, for a bit of background on this, I'm a second-year EPS student at Imperial College London, and I did this bit of research for my end-of-year project at the end of year one. And behind this title slide is the latest photo I believe we have of Venus. And this was taken by the Bepi-Colombo space probe on its flyby past Venus on its way to Mercury. And this was taken last October. So just a little summary on Earth and Venus first. So you can see here that the bulk properties of Earth and Venus are very similar. They have similar densities, surface gravities, and chemical compositions. So both are rocky planets with silicate mantles and metallic cores, and both formed in the inner solar system, so their chemical compositions are very similar. And what we can conclude here that their subsequent evolutionary divergence, that's really the result of the fact that Venus receives more solar radiation than the Earth. So the result of this has affected the way specific elements and compounds have been concentrated on Venus, so most notably CO2 and water. And this has produced a knock-on effect that affects the entire geology of the planet, so its mantle convection, its crust, and its atmosphere. And it's almost analogous to eggs. So if we have two eggs with the same mass, the same chemical composition, you can apply subsequent processes to them to make two very different end products. So in this case, a poached egg and a scrambled egg. And now we ask the question, why are we measuring argon on Venus? So argon is a good gas to measure because argon is always gaseous and it's a noble gas, so it's inert and it isn't affected by other geochemical processes. So it always remains in the atmosphere. Argon follows quite a simple migratory process on Venus, and the noble gases enter the atmosphere through volcanism, and they aren't subsequently react or sequestered, so they don't. They just remain in the atmosphere and accumulate over time. You might ask, right, why not measure helium? Because helium also fits these properties. There are two reasons why, and the first reason is because helium is less abundant on Venus. That means we have to apply more specific, better instrumentation, and we don't have this more sensitive instrumentation right now on Venus, so we can't do this measurement. The second reason is that helium is about 10 times lighter than argon. So this makes it more susceptible to atmospheric escape, and this complicates the modeling process because you have helium both entering the atmosphere and leaving the atmosphere at the same time. You might also ask, why not other noble gases? Because other noble gases like helium and argon, they also are chemically inert and always gaseous. This is also a question of instrumentation. Our instrumentation isn't sensitive enough to detect other noble gases either. So I guess we have to wait for more sensitive instrumentation to be deployed to Venus in the future. Now looking at depth in the isotopes of argon, we can say that there are three primary isotopes of argon on Venus. That's argon-36, argon-38, the two stable, two primordial isotopes, and argon-40, which is a radiogenic isotope, which is produced by the decay of rocks, potassium-40 in rocks, more specifically. And argon-36 accounts for 42%, argon-38 accounts for 8%, and argon-40 accounts for 50% of the total argon content on Venus. So if we look in more detail the argon cycle on Venus, we can see that it's quite simple. So the atmospheric concentration of argon-36 and 38 stays constant because they are primordial. They've always been around in the solar system, and so they were incorporated into Venus as it formed. And all the all the primordial isotopes of argon degassed during the magma ocean phase of Venus early on in its history, and therefore they are no longer inside Venus. The concentration of argon-40 increases as time passes because it's produced by the radiogenic decay within the Venusian crust and mantle. And this argon-40 is degassed by magmas and volcanism, and it's brought to the surface by diffusion as well. And to measure the abundance of argon, the total abundance of argon on Venus, we can assume that all the argon-36 and argon-38 was degassed in the magma ocean phase, and this means they are currently concentrated in the atmosphere. We can use the argon data that the Venera lander gathered, and the Venera lander determined that the concentration of argon-36 in the atmosphere was around 31 ppm. If we take the mass of the Venusian atmosphere to be 4.8 times 10 to the 20 kilograms, this means that there are 4.17 times 10 to the 17 moles of argon in the Venusian atmosphere in total. And if we apply this to Earth, a very similar planet with very similar chemical composition, we would expect there to be 5.07 times 10 to the 17 moles of argon on Earth, solely for the fact that Earth is 1.25 times more massive than Venus is. If we actually do these measurements, though, we observe that there are 1.19 times 10 to the 17 moles of argon on Earth in total. And this represents a 97.7% loss. So now we have to ask ourselves, how? What happened? How could this be? How did the Earth lose so much argon? And to understand this better, we can take a look at the other isotopes of argon. So more specifically, we're going to look at argon-40, the radiogenic isotope, which is produced from a different source as argon-36, but has the same physical and chemical properties. And if we look at the isotopes of argon on Earth, we can see that argon-36 actually forms a minute fraction of the total argon content. Argon-40 is overwhelmingly dominant in Earth's atmosphere, and in fact, it's 3 orders of magnitude more abundant. And this shows that despite significant quantities of argon-36 being lost, no argon-40 has been lost. And this indicates that the argon loss occurred before any significant quantities of radiogenic argon was produced by the decay of potassium. And this indicates that this argon loss, the loss of argon-36, occurred very early on in Earth's history. And this is supported by studies that show that argon-40 has been steadily accumulating in the atmosphere at a steady and unbroken pace since the Archean. And this was determined using gaseous inclusions contained within Archean and Devonian rocks. And these measurements in total suggest that there was a catastrophic high-energy atmospheric loss of argon-36 very early on. And the only event that could have feasibly caused such a loss would be the moon-forming impact, which occurred between 50 and 100 million years after the Earth first accreted. The kinetic energy of this impact would have caused a shockwave to pass through the Earth, so essentially the ground would have acted like a piston along the shock front. And this movement would have given gas molecules sufficient energy to escape the Earth's gravitational field. The impact would have blown off much of the primordial atmosphere if we take the value of 97.7% to reflect the loss of the wider atmosphere in total. And we can link atmospheric loss to the impact energy. And this was done in a paper by T.J. Ahrens, in fact. And he used a numerical model to link atmospheric loss to the energy of the impactor. And he did this for each terrestrial planet for a varying number for the polytropic index. So you have 2 values for each planet. And this constrained the impact energy to be between 6 times 10 to the 30 joules and 1.08 times 10 to the 31 joules. And from this impact energy, we can construct a simple model that relates the impact energy to the potential mass velocity combinations for the impactor, just by using half mv squared. So we did two calculations, a value for a straight collision and values for a 45-degree collision. And this really represents the two extremes of impact modeling in the Earth-Moon system. So most scientists generally agree that the Earth was hit by an impactor between 0 and 45 degrees. And the graph shows that generally the mass velocity calculations lie in the accepted range for the moon-forming impact. And this is that it was a body between half and twice the size of Mars, which traveled around or below the Earth's escape velocity, which is 11.5 kilometers a second. So, for example, if you look at the 45-degree collision, the calculations made imply that the impact will have been between 4.5 to 11 kilometers per second and would have been between half and twice the size of Mars. So if we compare this to other models, other people have also derived kinetic energy, mass, angle, and certain other parameters. They generally all agree with the constraints that were placed by the Argon data. You may get some more extreme results, and these may be produced where other parameters that haven't been constrained by the Argon data have been varied. And these may be things such as initial spin and whether the impactor collided with the Earth in a prograde or retrograde direction. And also note that not every study has constrained all three impact parameters. So this depends on their methodology and their aims. So for example, if we are using a chemical method to determine the mass of the impactor, then we can really only determine the mass of the impactor because the chemistry is independent of velocity and the collision angle. So in conclusion, the Argon depletion on Earth is a quite good indicator of the Earth's moon-forming impact. And this suggests that an overwhelming percentage of Earth's early atmosphere was lost. So as high as the high 90%, high 90s, so that's 97.7, 98%. Other researchers have also used this planetary comparison method. McHale and Heap did a study on Argon ratios as a proxy for volcanic degassing on Venus and Earth, and they found that the rate of volcanism on Venus was about, I believe, a third of the rate of volcanism on Earth in total. So there is definitely potential for new discoveries here, but in the case of Venus, to better understand, we have to acquire a better understanding of the planet before we move on, and this means collecting new measurements, sending new missions there. This can actually be done because the European Space Agency is proposing to send a mission called Envision, and the Envision mission to Venus is scheduled to leave in 2031. So there will definitely be more research on this in the future. So yeah, it seems that comparing two very similar planets is a valid method to determine differences between the two. And that's it. Thanks for listening, and I will take any questions now.
Thanks for that. That was a really interesting talk. So like Will explained at the beginning, if anybody has any questions, if you put them in the chat, I can read them out, or you can message me directly and then I won't say your name.
Saf, whilst people type questions, which I'm sure there'll be many, can I ask my classic opening question, which I always try and get in before the actual good questions come in? So I was just wondering, so I mean, this is obviously looking at the Argon data for Earth and for Venus as well. And from that, you kind of coming to the conclusion of pretty much all of Earth's atmosphere lost by the moon forming impacts. I'm wondering, you showed some of the different models that had been proposed for different studies of the impact. But do you have a handle on any of the other uses of other noble gases or other evidence that supports the same amount of atmospheric loss, or if there's any studies that maybe contradict that and suggest a different amount of atmospheric loss from the moon forming impact?
It's rather hard to actually constrain the actual amount of atmosphere lost, because there aren't many direct indicators that exist anymore, because this was so far back in the past, and because Earth's atmosphere has changed so much since the moon forming impact. Generally, I believe it's mostly modeled by these numerical models. I believe Arends actually used a 2D model subsequently, and this produced a similar value for atmospheric loss. So numerically speaking, yes, Arends agrees with me basically, but in terms of direct evidence, there is very little, and I don't personally see much direct evidence being dug up in the future. But I think the evidence currently points to the moon forming impact knocking off most of that early atmosphere.
Okay, so it doesn't look like there's any questions in the chat at the moment. If any come through, then I think what we'll do is we'll move on to the second talk, and then if any come through, Xiang, if you want to answer them in the chat, or we can kind of stay along at the end if people have questions then. But I think for now we'll move on to the second talk. So brilliant, thank you Xiang for that talk. And again, as I mentioned before, both of our speakers are from Imperial this week, which makes it easy for me to remember for introductions. And our second speaker is Ananya Mirchandani, who will be speaking to us about, I mean, obviously we've seen this week about Mars and lots of stuff going on there, but maybe Ananya will be speaking to us more about the moon and the potential for setting up some kind of permanent bases there and the prospects to do with that. So if you want to share your screen.
Perfect. Yeah, it's interesting that you brought up Mars, because all of our current work on the moon will actually take us there, because it's cheaper to test things out on the moon than it is to test things out on Mars. And I will introduce that topic later in my talk. All right, before I formally get started, I thought I'd show you some artistic visualizations. Also, please excuse me if I'm looking to my right or left, whichever that one is for you. I have my script here, just so I don't go over my time. I heartily believe that as aspiring scientists, we breathe the dreams of the future. I know that sounds cheesy, but since we already have Nike self-lacing shoes from Back to the Future, long-term habitation in extraterrestrial space should really just be a walk in the park. Just imagine the late 2020s, maybe 2030s, this could be the moon. I hope my talk today gives you an insight into the scientific appeals of a very small aspect of making this dream a reality. Hi everyone, my name is Ananya. I am a second-year geophysically inclined Earth and planetary scientist. I find it interesting, Xiang did numerical models and he's a geologist. I'm a geophysicist and my presentation is geology. We love that. Essentially, I hope to introduce you to the topic of solar sintering, something that I've had the opportunity to informally research for an engineering competition these past few months. Before I continue, I would like to acknowledge my team, Ramana, Sean, and Sujat from the Department of Aeronautical Engineering, as well as our academic guiders, Dr. Matt Genge, Mr. Stanley Starr, Mr. Josh Rosera, and Dr. Catherine Hadler, all from the Department of Earth Science and Engineering here at Imperial. What to expect from today? It's a very elementary discussion of the need of lunar masonry, learning about the environment and the geology on the moon, reviewing current research, as well as understanding the proposal for solar sintering. As we see a multitude of great leaps in the field of space exploration, there is an increasing demand to address resource accessibility and dependence in space. By 2024, Artemis, which is this really cool moon mission, you guys should read up on it, will be on the moon and we'll see humans returning to the surface. ESA too has plans of returning, but much more large scale, with a moon village by the 2050s. To support any plans of long-term missions, we need to incorporate efficiency, sustainability, and cost engineering into our scientific ideation. In fact, ESA has already begun working with Foster and Partners to plan building for the moon. We're looking at bottom-up printing of radiation and habitation shields over a blown-up cell. I don't think you guys can see my mouse. I can't see it. So the little white blob is the blown-up cell, and the gray material near it is what our rovers will sinter over this habitation cell, enabling radiation protection. In fact, this process has already begun trialing and testing, with the block on the left showing us an example of the lattice structure that is going to surround the the habitation floatee. Just give me one sec. Yes, so what ESA did was they used calcium, iron, magnesium oxides to mimic what lunar soils are like, which I will be referring to now as stimulants, because we don't have soil samples on the Earth, and that's why we're going back. So the gear ratio measures this relationship between the mass we need to launch things into low Earth orbit and eventually deliver that mass somewhere where we want to deliver it. And with respect to the moon, it will take 4 tons of propellant and material for just 1 ton of payload to be delivered to polar regions of the moon, which is where we're going with Artemis. Hence, with this massive ratio, it is so important for us as aspiring scientists to cater and consult engineers to be more mindful, especially for construction and economic purposes of space exploration. And this is done as we rely on ISRU. For those of you who haven't interacted with this before, ISRU is basically short form for In Situ Resource Utilization. It's a process in which we are able to harness products, which can be literally the solar wind, lunar soil, water ice, more popularly being explored right now, to do something with it. And essentially, that's what we're doing with really cool space bricks. So back to basics, how do we make bricks? So when we think back to basics, making bricks on Earth, we add water to cement as one of the many methods to do it. This is a process also scientifically known as additive polymerization, because it's just like an active research stream in brick making, period. Taking aspiration from such projects is so important. But the biggest drawbacks of using additive polymerization in space exploration is that the projects won't be independent of Earth source materials. So to give you context on that, are this really interesting project I found, because ISRO actually used a bacteria from urea. I don't know if I'm pronouncing it right, but it's bacteria from urine to actually make bricks on the moon, which is so cool, but also not what we're looking for. On the other hand, we also have a more extensive research conducted by Miranda et al. In 2017, who investigated the addition of thermoplastic polymer particles to facilitate the bonding of soil grains. What they learned is that gradation of the regolith is actually so important, because finer grain would enable more efficient polymer distribution at intergranular contact places, which is where the grains meet. So sorting grain size is an engineering problem. But as geoscientists, we need to figure out how to eliminate our dependence on that additional polymer, which is the cute little blob at A. And we need to figure out a method that we can reproduce The same effect that additive polymerization has, which is primarily what B is pointing at on this SEM image, and that's building these polymerized bridges that connect things together, which brings us to what exactly sintering is. There are several other methods of making bricks, but due to time, I'm only going to talk about solar sintering. So what is sintering? Simply put, it is the process of heating powdery material and substance into a solid form, seen here, powder into bricks. An interesting party fact is that Taylor and Meek in 2005 derived that theoretically, if we microwave regolith using just the power of a kitchen oven, we can reach temperatures of up to 1200 degrees Celsius, which would enable melting the regolith in just a few seconds due to the nanophase of iron oxide present in glossy regolith. I just find that hilarious. Like, it would be easier for me to melt regolith than boil a cup of water. How cool, science. Anyways, how do we justify that regolith is the perfect candidate for this job? So regolith is actually a very fine, granule, jagged, unconsolidated dust that covers the moon, and it's produced from rocks that have been pulverized and modified due to the lack of atmosphere. The upper 2 centimeter of regolith is actually known as lunar soil, and that's what is going to be of particular interest to us because it's loose. So we need to ensure our sintered brick and whatever we're making in the future caters to the lunar environment and the challenges we will face as humans. The main threats to human exploration on the moon include regular micrometeorite impacts, sustained solar radiation, solar winds, and temperature fluctuations. I'll just take this brief opportunity to do a quick lunar geology crash course. So the moon's geology varies greatly with location, and we have far too few samples to actually make a case for global geology. Macroscopically, the moon is split into anorthositic highlands and the near side, which is so much more important to us, which is what you see like when you look outside your window. And that dark region of the moon is actually theolytic basalt, forming these younger flat plains. So all of our samples from Apollo missions are actually from this area, showing us that silicon, the orange stuff on the pie chart, and the purple lavender color oxygen are the most abundant. And this will be very important in any instrument missions that you as scientists get involved with in the future. So just in conclusion, I'll come back to those points, but regolith becomes the perfect candidate just because it is abundant, easily excavated, and it has radiation protection potential. Most importantly, that high silica content is seen through the presence of agglutinates, which are basically glossy shard aggregates. And they make up 60% of mature soil, the top 2 centimeters by volume. And this is essentially what sintering feedstock will be in the future. And basically, as we saw on the previous slide, I will go to that, yes. Soil samples are these like heterogeneous, sorry, I got distracted. Hi, Tom. These heterogeneous mixtures made of agglutinates and other glossy particles with soil cloths cemented together, melted and fused together with this glossy matrix, which is probably the dark gray matter you see in the back, or equally the things that are labeled agglutinates. And yes, oop. There we go. So this is where it gets interesting. Marcus Kaser successfully performed a simple state-of-the-art demonstration using this on Earth-based sand and used a Fresnel lens to concentrate solar energy to perform 3D printing. Immediately, we can see that sand made of silica plus the sun gives us building potential. So essentially, that large volume of glass is of great importance. In a conversation with Dr. Matt Genge, I learned the key skills of going back to basics. Again, very important as a scientist. We talked about how in volcanic regions, explosive pyroclastic material, which is powdery, settles with temperatures of over 530 degrees Celsius, resulting into something called ignimbrite welding, making this degassed, non-vesicular dense rock that you see on the screen. Sounds a lot like what we need on the moon. I realized, however, there is a gap in sintering literature that doesn't actually address the geological processes that are taking place during the production of such a rock or brick. Using everything we've just learned, I've attempted to explain to you what is actually happening during this process. Along with my team, Xiang, Ram, and Sujat, we proposed the following. What our sintering mechanism looks to target is specifically those lunar agglutinates and ignimbrite deposits in lunar soil to mimic the natural terrestrial ignimbrite welding that I just talked about. So essentially, we'd be performing some sort of re-welding mechanism, whereas in the glass deposits in the lunar soil, represented as the silica solid grains on the screen, are heated to their transition temperatures, which we've assumed to be around 620 degrees Celsius. And then they get demobilized to become a melt liquid. And following that, there would be a reworking in the silicate boundaries of the particles by performing silicate polymerization without using additional polymers, as some oxygen is also removed. So essentially in this heating process, the non-glass components, so like the soil cloths and anything that's not glass basically, would actually weld in between this silica melt liquid and make a new brick similar to the one we just saw before of the ignimbrite. And this mechanism essentially will use the property of glass being a super cool liquid, which is when it is solid. We'll use the use of spontaneous cooling, which is just a second order reaction that does not need any activation energy to create this aggregate matrix with embedded mineral crusts, also known as our modern lunar brick. For credibility, I thought I'd explain that similar sintering experiments and mechanisms have been demonstrated. The most extensive, however, being through the European Union's Horizon project with Regolite, which use solar ovens with concentrated xenon lamps, which is labeled in the diagram to the left. Using this stimulant, Maurice et al. Proposed a technique that allows sintering of a brick that you see this hand holding in just 30 minutes. And I know 30 minutes seems like a long time, but everything is at such an early stage of conception that 30 minutes is still a great feat. In fact, this technology that ESA and the European Union are developing has already reached TRL5, or it's progressing its way to TRL5, which is essentially validating these results in the appropriate environment. And I found this incredibly cool, but space is a vacuum essentially, and this research has found that vacuum conditions act as an advantage to performing such procedures, because lower temperature and space will require the grains, will cause the grains to bond together. Oh, sorry, what am I saying? They bond together easier than in air because the lower temperature prevents that additional porosity, which is just apparently like an intrinsic chemical property, a physiochemical property. So our project essentially builds on these ideas and marries the Fresnel lens and ESA's research to produce an engineering proposal of how to execute this more efficiently. So just as a reminder, the ESA project didn't use a lens, they used an oven, and we used a lens. So with our theoretical calculations, we, to our surprise, calculated that it would just take 19.6 watts to make a brick that's like 5 by 5 by 2.5 centimeters, which is crazy because that's the same amount of power you need to light like your lamp. We can see here with the bottom calculation, number 5, that there's abundant solar flux density on the moon to actually facilitate and provide energy for this brick making. And how efficient have we been? By repeating this process layer by layer, we've calculated that it would take us 50 minutes to build this brick. Indeed, 50 minutes is more than the 30 minutes that Regolite has proposed. However, we still will execute over half of the solar oven's efficiency despite being much more simplified. Theoretically more feasible, more energy efficient, and potentially cheaper too. So why doesn't research in this field have diverse approaches and has significant gaps? Because of course, with anything in this space, there is rigorous capital demand. We also don't know the geology of the moon, and ISRO applications, whether you're making bricks or understanding water ice, rely heavily on the local geology of where your mission will be deployed. And lastly, this is an unexplored field, so there are undefined research boundaries, which means there are a host of different brick-making technologies and techniques, and you can't really compare them because they use different things, they have different parameters, and they produce different results. With respect to compressive strength too, for example, the ISRO brick apparently had 10-fold strength, compressive strength to conventional bricks, because it used something called guar gum, which is a bacteria that you find on Earth, whereas the Regolite brick was just 5 megapascals. And when you compare these two, you can't say that the ISRO brick is better because it's of course not independent of Earth resources, hence explaining why things are hard. I am just finishing up, do not worry. So what's next for our bricks? There are so many problems we as scientists need to solve before we can commercialize anything to do with brick making. There is limited proven material related to the mechanical properties, as I've explained. We'll have problems about surface coating, precision geometry of actually building our bricks or building the structures around them, and so much more. One of the most prominent for me is activity during the lunar night. Most missions are going to the South Pole. Sintering may not be an ideal solution for the South Pole because of the positioning of the sun, which is something important that we as geoscientists also need to think about. However, I'm sure we will figure it out. So 2 more exciting futures. What is happening down our brick road? I found that so funny. Anyways, we are going to build our first lunar outpost by the time we probably all graduate with our PhDs. Exciting. And ESA will have Lunar Village up by the 2050s. We're redefining design engineering not only for the space, but also for here on Earth. We're looking at tessellating bricks and creating skeleton structures. And essentially, the most important part of sintering research, considering how novel it is right now, is its applicabilities in paving moon roads and sintering out launch pads. So when you launch a rocket off the moon, there isn't too much dust that's flying around because you've paved the whole thing. And Ad Astra, which is to the stars, because there is so much more potential. Anyhow, I could of course go on and on talking about this topic. However, I am opening the floor up to discussion, and I say discussion because this was my very first science talk on a topic that I've never formally researched before. That's true. I have prepared an archive of resources if anyone is interested in further reading. So please don't hesitate in reaching out to me. I realized I have not put my email up, but you can find me on LinkedIn. Thank you so much for your time and support. I hope you learned something new and you laughed at some of the amazing jokes I made. Have a very good evening. I'm opening the floor to any questions. Thank you.
Thanks for that. That was a really exciting talk, actually. So yeah, if anybody has any questions, same as before, put them in the chat.
I can't see the chat, so I love that.
So I was just going to start with one, which is a question that definitely doesn't reflect all of the interesting things that you've spoken about. So I apologize, but I was just kind of curious about the Artemis mission. If you know why they're preferentially sending stuff to the polar regions, do you know if there's a reason for that?
Yeah, so the polar region is of a special interest right now due to the water ice potential that's up there. Due to crater shadowing, we have frozen water at the polar ice caps, at the polar caps. And essentially the biggest ISRU research that is going on is how to extract hydrogen and oxygen from not only lunar regolith, but from that water ice. Because once we get that oxygen, we get that water, we're sorted for life systems, life support systems on the moon. We'll have fuel for our rockets, we'll have water and oxygen for our breathing. And that's why Artemis is focused on the poles. And when we do go, we're going to be living off the Earth, or we're going to be living on these things called the human landing systems, which are just landers for a period of, I'm not too sure how long, I think up to 10 months.
So we have our first question in the chat. So would it not be very difficult to ensure that lunar bricks hold themselves together compactly because the regolith is ionized and charged?
That is very, very, very true. It is one of the challenges we are facing, and I am not a material scientist, so I can't comment on that greatly. But from my understanding is, when you sinter something, some people argue that sintering does not take it to its melting temperature. However, what we're doing is we're almost burning or melting something and putting it back together. So technically, yes, parts of the surface of the bricks would wear off and fall apart. However, the large-scale structure should theoretically stay in place if we crack the strength requirements. Yet I did mention in this slide that surface coating is something that could protect us from how the ferromagnetic regolith actually responds to the external features. And there was also this interesting research paper I read. I will try and find it, but it's actually, I think it's Taylor and Meek who talked about how ferromagnetism and how even the ionized properties are affected by the grain size. And of course here, I'm not looking at actual grain size of the regolith, but if you make a boulder of this regolith, the ferromagnetic properties essentially should decrease. That's what Taylor and Meek propose. However, a short and simple answer to your question is yes. Theoretically, it would be very hard. However, we're not going to start making bricks until we can solve that. Yeah.
Brilliant. So at the moment, there's no more questions again in the chat. In fact, oh, hang on, I think one's just come in. In fact, there's two that, okay, I will shut up. Safi can go back to asking questions.
Okay, so Peter asks, he says that's a really interesting introduction to moon bricks, thank you. Has there been progress on moon mortar? What might be a good way of sticking the bricks together?
Did you say moon water?
Mortar. With an M.
Oh, mortar. I'm so sorry, my English suffers sometimes. Mortar is like a cement mix, right? Or?
Yeah, it is.
So basically, it is very easy to conceptually just be like, why don't we take the regolith and put stuff in it and make it sort of something like a cement? And it's something called lunacrete, but it's not as widely looked into because it's harder to work with and also requires the addition of like oxygen. I know for sure you'll need oxygen, even though it is present in the, so I've written here, bricks are for building blocks. Concrete is dependent on oxygen and water. So lunarcrete or mortar would be dependent on actually getting water or hydrogen and oxygen in some sort of chemical positioning that would change the chemical properties of the regolith. And there hasn't been too much work that I'm aware of. Personally, I think it's smaller institutions that are conducting this research because there's low pay for low turnover for any time you put into this research. But if you'd like to do further reading, Lunarcrete, like Lunarcrete, like concrete, but Lunarcrete is a good place to start. All right.
The second question in the chat is, do you know if any consideration has been given to moonquakes and the bricks/lunar village?
You know, that's a great question that I do not know the answer to. I'm not so sure that that I have considered it. I'm not actually sure about anything about the seismics of the moon, which is a great feedback for me because I will go read up on that for sure. And hopefully you can too, unless you're happy to message me privately and I can let you know what I find out, but I'm not too sure at all. Now I'm thinking about it. I'm like, so what do we do when we build something on the moon and then there's a moonquake? But then how strong are moonquakes? But I'm sure Artemis has thought of it. So I'll look into that.
Brilliant. Okay, I'll try again and say that there's no more questions in the chat. Inevitably about 5 will come in as I say this. I think actually in terms of the moonquakes thing, moonquakes are generally they're not that strong, but they also occur in very specific regions in these kind of nests where they occur, but so it's not as kind of sporadically distributed. So maybe there's some potential for just avoiding those regions of near surface magnitude. But anyway,